A 10-kilogram block is placed on a 30-degree incline where it sits without sliding, as shown in this figure. So we're going to start with drawing the free body diagram. So we have a downward force of gravity. It's on a slanted surface, so the normal force is perpendicular to the surface. And there is friction preventing it from sliding down the ramp, so the friction is directed in the opposite direction, up the ramp. The normal force and the frictional force are perpendicular to each other, and the gravity is kind of separate from those, so when we resolve these into components, it is better if we rotate the axes first to line up with the frictional force and the normal force, and then we just have to break gravity into components. So, 3 forces on the box. Part B, are the forces on the block balanced or unbalanced? And you know this by now because the block's not moving, the forces are balanced. Part C, to calculate the magnitude of the frictional force on the block. So let's look at what would happen if we break this into components. So I'll draw a X and a Y axis on here. So these dotted lines represent the rotated axes. So that's your X axis and your Y-axis, and if you do some geometry, you will find that the angle FG makes with the Y-axis is the same as the angle of the ramp. So when we break this into components, I'll draw a separate free body diagram, and we'll have the normal force still directed that way, and the frictional force still directed that way, but now the gravitational force, since it's going straight down between these two axes, part of it's going to be on this axis and part of it's going to be on this axis. This is the one closest to where the angle theta is, so this one's going to get the cosine. So we'll say that's FG cosine of theta, and down this way is FG sine of theta. So it's necessary to do that and break it into the components first before we solve for part C. Now let's look at part C. If we do the sum of the forces in the y direction equal to 0, since forces are balanced, that would tell you that the upward normal force balances out with the downward component of gravity. So Fn is equal to Fg cosine of theta, and then because we know the normal force now, because we can just plug in the formula, Fn is equal to mg cosine theta, which is the mass is given as 10, gravity is 10, and cosine of 30 is root 3 over 2, so it would be, we could get a numerical value for the normal force. And then you know the frictional force. The equation for the frictional force is equal to, we're dealing with static friction, Us times Fn. But here's the issue now. What you're doing is you're trying to solve for the normal force first, using this equation, and then plugging it in here when you don't actually know the coefficient of static friction. And the other thing is, this is actually not a correct formula, because the correct formula for friction is that this is the maximum static frictional force. So even if we did know what that US was equal to, this formula still would not work. So I want you to be aware, because that's a really common mistake that people make, is trying to go through this process to solve for static friction. The true way to solve for the static friction force is to remember that with static friction, the forces are balanced. So what we actually need to do is focus on the x direction and balance this force with this force. So we're going to say that the net force in the x direction is 0, which allows us to set the static frictional force with the gravitational force times cosine or times the sine gravitational force, times the sine of theta. So that's just going to be mg sine theta, which is 10 times 10 times the sine of 30, which is 1/2. So 100 times 1/2 would give you a static frictional force of 50 newtons for part C. Now in part D, if you look back at homework question 7, part F, it says the coefficient of static friction cannot be calculated using the information given because we don't know if we're at where we are. It could be anywhere up to that maximum value. But it is possible to determine a range of possible values for μs that's a bit more specific than just saying that μs is between 0 and 1. So the way we can do that is, if we now look at one of the true formulas for static friction, one of the formulas we saw was that the static frictional force is less than or equal to μs times the normal force. And if you rearrange this equation to get μs by itself, μs is greater than or equal to the frictional force over the normal force. And we've already got an equation for the normal force. We did it up here. So we can just put that in as FF over mg cosine of theta, and plug in these numbers. The frictional force, the true static frictional force that we have, is 50 divided by 10 times the cosine of 30. Just plug all this in your calculator and you'll come up with an approximate value of 0.58. So what this is now saying is that μs, the coefficient of static friction, is greater than or equal to 0.58. And that should make sense, because if μs was a number less than 0.58, that means the surface is not quite as sticky, so the block might slide down. But if 0.58 is a valid coefficient that works, any coefficient that's bigger than 0.58 but still less than 1 would also work. So the answer for part D, what we're going to say is that μs is between 0.58 and 1. And we're just going to finish up with a few conceptual questions. So if we assume that the coefficient of static friction is the lowest possible value in this range, so μs is now going to be equal to 0.58, then the block is given a slight nudge, which causes it to slide down the incline. So part E, the instant it is nudged, does the frictional force on the block increase, decrease, or remain the same? Well, basically, you're turning static friction into kinetic friction by giving it the nudge. And since you know that kinetic friction is less than static friction, that means that the instant the nudge happens, the frictional force is going to decrease simply because it's changing from static to kinetic friction. Part F, are the forces on the block balanced or unbalanced after the nudge? Well, if you look at this diagram that we drew over here, you remember that the frictional force and this component of the gravitational force were initially balanced right before the block went down the incline. But when we nudged it, this frictional force became a little bit less, which means that this force staying the same and this force being a little bit less are no longer going to be balanced, because the downward force, the force going down the incline, is greater than that kinetic frictional force. So that's why they're unbalanced. And then unbalanced forces in part G leads to the block, instead of moving at a constant velocity, which is all the balance forces that we've been doing for the last few weeks, the block is now going to accelerate or increase in speed as it goes down the incline. And you don't have to justify the answer for part G, because we're only just starting that now.